Bonjour. Donc, nous avons aujourd'hui l'honneur d'accueillir Guy Perrin pour nous parler de Gravity. Alors, on m'a donné la lourde tâche de vous le présenter. Alors, bon, je connaissais un peu Guy, on se connaît depuis un certain temps, mais j'ai eu la chance d'avoir aussi un anti-sèche, parce que Guy a fait l'objet d'un article assez élaboré du Point en tout début d'année. Donc, j'ai eu mon anti-sèche, j'ai été lire cet article pour savoir ce qu'il en retournait de la carrière de Guy. Et ce que je peux vous dire, c'est que Guy a fait ses premiers pas en astrophysique, ici même, à l'Institut d'astrophysique de Paris, en faisant un stage de l'X. C'était dans un bureau qui était juste derrière, à l'espace où il y a actuellement l'accueil et l'espace de Valérie Bonnat, pour ceux qui connaissent.
C'était à côté des toilettes. Oui.
À côté des toilettes, voilà.
C'était stratégique et bien placé. Oui.
Et c'était un stage sur Beta Pictoris. Alors depuis, il y a certaines personnes qui continuent à travailler sur Beta Pictoris, ils n'ont toujours pas fini. D'autres ont évolué, et c'est le cas de Guy qui a travaillé sur Fluor, d'abord, donc les développements de Fluor pour l'interférométrie avec des fibres optiques. Ensuite, il a aussi travaillé sur la combinaison des télescopes à Hawaï, et ce qui me permettait de dire à l'époque qu'il avait les plus grosses jumelles du monde, avec les deux télescopes Keck, ça fait une superbe jumelle. Et puis, donc, en lisant cet article, j'ai découvert que tu avais été honoré du Grand Prix scientifique d'El Duca par l'Académie des sciences. Actuellement, tu es directeur adjoint scientifique à l'INSU. En quelque sorte, c'est notre patron à nous tous. Donc, mais ce n'est pas à ce titre-là que tu viens ici aujourd'hui. C'est pour les développements de Gravity. Et donc, je vais te laisser nous présenter Gravity. Et voilà. Merci.
D'accord, merci beaucoup. C'est en français ou en anglais? In English. Okay. Thank you very much, Alain. I have to say that Alain should feel very guilty because without Alain, I would have never done any astronomy at all. It was not my career path initially. And Alain told me when we were sitting on the same benches at École Polytechnique that there was a very nice training course in IAP on Beta Peak, and then I came with him. We did fantastic research for 2 months, the first steps in research. And eventually I had a PhD, and eventually I had a position, and well, that's it. So thank you, Alain. And thank you, IAP. And Alfred and Roger Ferlet, that I should not forget. Okay, so I have to apologize first because most of my slides are in French, not in English. I simply didn't have time to translate most of them. And I did new ones in French also, since they were all in French, essentially. So I will give some insights of some of the results we've recently got on the Galactic Center with an instrument which is called Gravity. Gravity is an instrument installed on the VLT in Paranal at ESO. It's an interferometer, a large interferometer. And the idea of Gravity was to get enough angular resolution to look at a black hole at the scale of the horizon of events. So that's the basic idea. So I will start first with an introduction to the scientific case and with what was done before Gravity, and then I will show the results we've got with Gravity. Only on the Galactic Center. Gravity can observe many things, late-time stars, possibly exoplanets or young stellar objects or quasars, AGNs, etc. And I will focus only on the Galactic Center. Okay, so this is our galaxy seen by an infrared satellite. And the region by which we are most interesting, of course, is the Galactic Center, which is in the center of this bulge here. The Galactic Center actually is a very complex environment. It looks like a spiral galaxy at the center, but that's pure chance. So it is called, this structure is called the mini spiral. It has a scale of about 2 parsecs. And the scale on which I'm going to concentrate first is the internal parsec of the Galactic Center. And then I will focus on the hundredth or thousandth of parsec at the Galactic Center. So around this mini spiral, you find a circumnuclear disk of gas and dust on a scale of a few parsecs. And in the middle of this circumnuclear disk, you find star clusters. And some of them are arranged in disks. That's the case of these two star clusters here. You have about 100 stars, massive stars, OB stars, and Wolf-Rayet stars. And so this is at a scale of a bit less than a parsec. And at the very center, you have another cluster, which is called the S-star cluster, which are massive stars, again, but on the main sequence. And there are about 50 of them. And these are the closest stars known to the galactic center. And at the very center, of course, you have the galactic center itself. So this object called Sgr A, which was discovered, Sagittarius A star, which was discovered in the radio domain in the 70s. A, because it was the brightest source in the radio in the Sagittarius direction, and a star because it was seen as a non-resolved radio source, which was not very difficult at that time, but it was still a non-resolved radio source. And of course, there is a strong belief that this object is a supermassive black hole with a typical Schwarzschild radius of 10 microarc seconds. And this 10 microarc seconds, of course, is the scale of interest here that sets the, oops, sorry, everything is automatic, that sets the scale at which to which we need to access with gravity to study the black hole at this event horizon scale. So that gives you an order of magnitude of the challenge that we need to solve to address this scientific case. Okay, so now we come to the problems. If you look at the inner 1 arcsecond here, closest to Sgr star, and you make an observation in the infrared with a telescope larger than a few tenths of centimeters, this is what you get, whatever the size of the telescope, essentially. And while this is a very well-known effect, this is due to the very bad influence of atmospheric turbulence that blurs the images. And what you would like to see in this central arcsecond here is individual infrared sources, stars, in order to try to measure some trajectories. And of course, if you don't have enough angular resolution, you cannot resolve individual stars and you cannot measure trajectories. So to do that, you need a miracle system. The first part of it is to have access to very large telescopes. For us Europeans, that's 8-meter telescope, the VLT, in Paranal at ISO in Chile. Why do you need that? Because the angular resolution scales, that's the laws of optics and of diffraction, scales with the size of the telescope. So the larger the telescopes, the better the angular size you can access. So that's the first part of the miracle, and I don't know if you've seen an 8-meter telescope, but when you see it work, you understand that it is a miracle to have that today as astronomers, because these are fantastic machines. The other part of the miracle is this. It's called adaptive optics, and I can assure you also that when you see that working, that is a miracle, because it works exactly like that. So you see the images here are disturbed by turbulence. If you were limited by the diffraction, you would have this scale for the image, and the image is blurred due to turbulence and moves at a pace which is on the order of a few milliarc seconds up to 10 milliseconds, sorry, that's time, not space, 10 milliseconds, which means very, very fast, unfortunately, which forces you to make short exposures, and so your sensitivity drops down dramatically. Now, if you turn on the adaptive optic system, boom, this is what you get. And honestly, well, this is a simulation, and there's no noise here. But this is a physical simulation in the sense that it was made with the internal source of the adaptive optics, the first adaptive optics system for the VLT, which was called NEOS, or NECO for the instrument. And there was an internal simulation of turbulence. And so all the scales that you see here are correct on the sky, except on the sky you have the noise added on top of that. So this is what you get when you close the loop. you get an image which is much more stable, and you immediately recover the angular resolution of the telescope. You're not limited anymore to an angular resolution of on the order of a fraction of an arcsecond in the best sites. Then you get to an angular resolution of a few tenths of milli-arcseconds. So that's a considerable gain. And of course, if you have multiple sources in your field, then you have a chance to separate these sources as long as they are distant than more the angular resolution of the telescope. That's the definition of the angular resolution of the telescope. Okay, so now we have this tool. We turn the magic on, and when you look at the central arcsecond of the galactic center, you can resolve this blob here, these blobs, into individual sources. And the closest you are to the galactic center, and the more motion you get in a limited amount of time. So this was done immediately after the NEOS system was available at the VLT. So this was done by a consortium which was part of the NEOS consortium. And they started to monitor the motion and the orbits of stars at the galactic center. And the first one that was, the first orbit that was convincingly measured was the one of the star called S2 here, which is going to play a very important role because S2 is the star closest to the black hole that we know today. And it has also a very nice feature. It is on a very elliptical orbit. So the eccentricity is very high. Almost 0.9, which is very important to detect relativistic effects. So that was the first time an orbit was measured at the galactic center, and immediately after that, of course, you can deduce, using the third Kepler law, you can deduce the mass of the black hole. So there was a first estimate of the mass of the black hole at that time with this first orbit. But there is a way to go further, because with the adaptive optics system, you do images, and so you have 2D information on the trajectory of the object. If you want to have a full information, you need the third dimension, and the way to do it is to do it by spectroscopy. Well, you are very familiar with that, of course. And this was done actually with another instrument called Symphony. There's an equivalent on the Keck, whose name I have forgotten immediately, of course. Sorry for that. Maybe some people know it in the room here. And this instrument was built several years later than NACO, and was more sensitive and allowed to do a spectroscopy on a larger amount of stars around the galactic center. So Sagittarius star is here, and you see S2 at that time was here. So they were able to, this may be not fully useful, just to tell you that these measurements were used on bracket gamma and on helium lines in the K-band with Symphony. So the advantage, of course, of doing that is that you get a 3D information on the S-star cluster, and you can resolve some ambiguities. There's also one hidden parameter when doing that, is the distance of the galactic center to us, which is a free parameter when you fit the data with orbits. And so that led to a very precise estimate of the mass of the central object. Not yet the evidence that this is a black hole, because the closest distance of S2 to the central source is about 1,000 Schwarzschild radii, which is not enough to constrain the mass to be inside a Schwarzschild radius, but still, compared to previous experiments, the scale at which it was constrained was much higher. And so you see here the mass of the black hole was estimated to be something like 4 million solar masses. So that's not the most massive of supermassive black holes. That's one of the smallest one. Well, depending on where you set the scale for supermassive black holes. But still, that's the closest one to us. And since the size of black holes, the size of the event horizon scales linearly with the mass of a black hole, while this one has clearly the largest angular scale on the sky. So the Schwarzschild radius for this type of mass is 10 microarc seconds. So that gives you a diameter of 20 microarc second for the event horizon. And with lensing effects, that translates into about 50 microarc seconds. So thanks to general relativity, we gain a factor 2.5, which is very important for us and very nice. So the other thing is the distance of the galactic center, and this distance was measured also accurately with these fitting by orbits of the data. So about 8 kiloparsecs. Okay, so this was done already 10 years ago. So what's next? Well, there are many things to be done still on the galactic center. Some at 1 milliarc second scale, and some others that request a scale comparable to the size of the black hole. So at this scale of 1 milliarc second, which is about a factor 50 improvement compared to what we can do with an 8-meter class telescope, what we can do is try to start to study relativistic effects using the orbits of the stars closest to the black hole, and also to understand the nature of these A stars and their distribution. There is a mystery, which is that all the S stars are young stars and massive stars. And there is a difficulty to understand how you can, first of all, only fabricate massive stars in the environment of a black hole, and how you can fabricate stars which have essentially the same age in this region of the galaxy. So we hope also we're going to learn more about this S-star cluster by measuring their orbits at a high accuracy. Now, at the scale of the black hole, of course, there's the idea that we want to show that Sgr star is really a black hole and there's no alternative. And for this, we need to get to the horizon scale. We want to understand the nature of flares. There are flares observed at the galactic center, and that will be part of the presentation today. And the black hole is also a unique laboratory to study general relativity in the strong field regime. So by measuring orbits of flares, for example, next to the black hole at the scale of the horizon. But of course, the challenge here is this. We need to get to a scale of 10 microarc seconds, or a few tenths of microarc seconds. That is to say, 1 Schwarzschild radius or a few Schwarzschild radii. Okay, so the trick is to go for a bigger instrument. Well, this is quite simple in principle. Since the angular resolution scale with the size of the instrument, just use a bigger telescope. Well, so far, telescope sizes are limited to 10 meters or 11 meters, so we need to do differently. The idea is to use an interferometer. This is a very, very old idea since the 19th century or even 18th century. And so if you combine the 4 8-meter telescope, they are separated up to 140 meters. You get the equivalent, not in sensitivity, but in angular resolution, of a 140-meter telescope. And this is how you get to an angular resolution of a few milliarc seconds in the infrared, because we are observing at 2.2 arc second in the K-band, between 2 and 2.4. For sensitivity reasons, the Sgr star is in a region which is extremely red due to the large amount of dust that obscures the object. And the K-band is a good compromise between sensitivity and angular resolution. It's also a good compromise with respect to the flares, because the flares have a tendency in the infrared to be bright around 2.3 microns. To do gravity, you need to make a very complex instrument. You have you have a beam combiner, so this is where the 4 beams of the VLT are combined in the instrument. The instrument is fully cooled down for maximum sensitivity of the infrared detectors in the K-band. It's also under vacuum for maximum stability. I was mentioning this scale of 10 microarc seconds. We will access this scale by astrometry. And to access that by astrometry, you need a stability of the path at the scale of 1 nanometer. And this is from that point here, the beam combination, up to the telescopes, or a few nanometers. That's the order of magnitude. And so to achieve that, you need to be extremely stable. But on top of the instrument, you also need adaptive optic systems. So we're not doing directly imaging with the 8-meter telescope, but we need to do interferometry, which is also imaging. And for interferometry to work with 8-meter telescope, you absolutely need to correct the images with adaptive optic systems. And for the Galactic Center, we need infrared adaptive optic systems because the sources are bright in the infrared. And there was no infrared adaptive optic systems for the 4 UTs at the VLT, so we also had to build 4 adaptive optic systems working in infrared. And to do astrometry and phase reference imaging, you also need to connect the entrance pupil of the telescopes with the interferometer by measuring in real time the optical path in the instrument. So we have metrology systems that come down from the 8-meter telescope entrance pupil down to the beam combination point here in the instrument. So we have, in practice, 8 metrology beams going away from the beam combination points in the interferometer and going up to the entrance pupil of the telescope. So gravity is a quite complex system. Actually, you have all the subsystems you could imagine in interferometry. They are now in gravity. So that's very nice from a theoretical point of view. But of course, the problem is that the instrument is more complex. The more subsystem you add, the more complex the instrument is. And beyond the goal to access to this fantastic accuracy and angular resolution, one of the challenges of the instrument was also to make sure that all subsystems would work together when we are on the Galactic Center. And at the time when we decided gravity was in 2005, interferometry was not that mature yet to be honestly 100% sure that it would work at the time we would be on the Galactic Center. So that was part of the challenge. Another part of the challenge, I actually took this photograph last week in Paranal. We had the ESO Council in Paranal. And this is the gravity cryostat here. You have the 4 beams who feed gravity, boom, boom, here. And I took this photograph with the DG of ESO, Xavier Barcons, and the director of the observatory, Andreas Kaufer, because I think it's a symbolic photograph. The first thing we said when we presented the instrument to ESO 13 years ago was it will not work if we don't work with ESO. It's not a contract between a consortium and ESO, but we need also, since it will be a complex system, we need to work with ESO. Apparently the idea was a bit genuine at the time, and we were very fortunate that it was well understood, and that now this instrument honestly is built by a consortium to which ESO belongs. And that has been very instrumental and important for the success of the instrument. Okay, so this is a list of names for the consortium. I show this list of names to show the logos, of course. You have 2 labs in France who participate to this instrument, IPAG in Grenoble and Lesia at Paris Observatory. This is my lab here. Onera participated at the beginning of the studies. And so in red here, you have the French names, or the names of the people in the French institutions. And you see that we are quite a good fraction of the consortium. Our contribution to the consortium was quite simple. It was interferometry. While others brought many, many things, what we had was the expertise in interferometry. And the consortium is led by MPE, the Max Planck Institute for Extraterrestrial Physics in Garching, and the PI, Frank Eisenhower, is from this institute. And you have Cologne also, Heidelberg here, Porto and Lisbon in Portugal, and ESO. You have the faces of the coais here. So the PI with the crown is the big boss. Karine Perrault in Grenoble, a photograph taken in Paranal. This is where she wears a helmet, myself. The colleagues in Portugal, Cologne, and Heidelberg. So it's a real European instrument with a strong French-German connection. Okay, so now the principle of the observation of gravity is the following. So one major feature of gravity is reference sources. We need reference sources. And we need two reference sources, or at least two. We need one, so this is the central arcsecond of the Galactic Center here. This circle here is two arcseconds in diameter. We need one source for the adaptive optic systems. And this source needs to have several very nice properties. The first one is that it has to be nearby the Galactic Center. This source is at 7 arcseconds, 6.5. It has to be bright for the adaptive systems to work. The adaptive systems work at a pace which is on the order of a few hundred hertz, sorry. So that means very tiny exposure times. This is hence the idea that you need brightness for this source. And it has to be point-like at an angular resolution of an 8-meter telescope. And so there are many miracles in gravity. And so one of the miracles is that we have this source, which is bright enough. It's the source of the 7th. It's 7 arcseconds away from the Galactic Center. It has a magnitude of k equals 7, and its name is RS7. So very easy. That's the only source for which it works. Okay, so that's the first source with which we can servo the turbulence at the scale of the 8-meter telescope. And then we need to servo the interferometer, because we have the same problems with turbulence at the scale of the interferometer. With the interferometer, you make fringes, and these fringes wander because of turbulence as well and vibrations. And so you need to have a reference source that will allow you to fix the fringes with what is called a fringe tracking system that we did in Meudon. And for that, the Galactic Center also is a unique case because you have several stars whose magnitude should be enough, well, now we know it is enough, to serve as reference for the fringe tracking system. And when you've done that, then you have stabilized the turbulence at the scale of the interferometer plus at the scale of the unit telescopes of the VLT. The fringes do not move, or they have slight motions, and then you can integrate, and this is how you can get down to magnitude 15, 18 on the Galactic Center. And of course, for this to work, you also need that these sources be unresolved, but now at the scale of the interferometer. The angular resolution of the interferometer is a few milliarcseconds, so the source has to be tiny. For example, if the source are binary objects, then probably doesn't work. So part of the suspense also was to detect immediately if these sources were resolved or not when we were able to do fringes on these objects. Unfortunately, they are not. And they have to be close to Sgr star to be in what we call the isoplanetic patch, that is to say, in a region of the sky where the properties of turbulence in real time here on Sgr star are the same as on the two reference sources. So far, so good. Everything worked extremely well. Now, the only suspense was to know whether we would be sensitive enough to fringe track on these sources. It has never been done before. And that was our first observations in May 2016, when we pointed at the Galactic Center for the first time. After making fringes for the first time with the UTs, we could immediately track on these sources. So we were absolutely relieved. It was a huge relief for us, because we knew that then we would have a chance that things would be possible. Okay, so that also explains why the system is quite complex, because you have all these cascade of reference sources plus the metrology on top of that you need to master and to have them work together in real time to be successful. You mean is there any other black hole?
Yes.
Honestly, we don't know yet. No. We, from the gravity results, we don't know yet. And anyway, they could not have been good references. But interesting from a science perspective, of course. Okay, so the way you do imaging with an interferometer is quite similar to the one you do imaging with a single telescope, except that the pupil is a bit strange, I would say, for regular astronomers, which I am too. But you can understand that you do imaging with an interferometer. Now, I would just like to focus on the principle of narrow angle, high accuracy astrometry with an interferometer. The principle is also quite simple. You need to have two fields in the interferometer. So the interferometer has to be able to do fringes on two different objects with the 4 telescopes, and therefore with a set of 6 different baselines. And so for each of these baselines, you get 2 fringe patterns here. And the distance between these fringe patterns here, between the center of the fringes, or the fringe patterns here, is proportional to the angular separation between the 2 objects projected on the baseline. So for each baseline, you are sensitive to the angular separation of the object in the direction of the baseline. Let's put it this way. And this is multiplied by, well, the optical difference you find is multiplied by the baseline. So to do astrometry, the idea is very simple. You divide this quantity by the baseline, and you get the angular separation. That's what you see here. And to be able to do that at an accuracy of 10 microarc seconds with a baseline of 100 meters, you need an accuracy of a few nanometers on the separation here of the fringes. So this is why we need to stabilize turbulence. Turbulence would set the fringes in motion here with an amplitude of the order of several microns, which is 1,000 larger than the accuracy we want to achieve. And of course, we want to integrate. Well, you also need to have a very good accuracy on your baseline, and this builds with the amount of observations you make. It's like when doing a pointing model with a telescope. The more stars you observe, the more your pointing model becomes accurate, and the more your accuracy for the pointing turns to be good. It's the same with an interferometer. And for practical reasons, we need something like 100 micron of accuracy of the separation between the UTs at parallel. Okay, so that's the principle of interferometry, of doing astrometry with interferometry. So I'm going to show you an example first with, let's say, a simple object, which is a nice binary star. Well, this one is interesting because people are looking for planets around these stars, this star, and to look for planets, you're going to look for the motion in the plane of the sky induced by the presence of the planet, which will be a departure from this very nice elliptical orbit. And for 1 Earth mass planet, you need an accuracy of 10 microarc seconds, which is the goal of gravity. So this is why we picked up that one. And what you have here, I'm not sure this is all visible. Do you see these points here? Okay, so this scale here, these are the dates, and it starts in the late 40s, 1940, 1950, and this is today. Okay, so this star has been this binary has been observed for many, many decades actually, and you have many, many points that allow to constrain the orbit. The circles here give you the error bar of the 2D error bar for each of these measurements, and here you have the error bar per axis. And the black point here are at the era of adaptive optics, and these gray points here with the large error bars are at the era before adaptive optics, so fully limited by turbulence. So you see already the great improvement provided by adaptive optics here. And the blue ones here are the new gravity points, okay? So we've been measuring that object since 2016. So not with the UTs in this case, but with the ATs. They are not corrected by adaptive optics, which will not be the case soon. There are tests happening these days to commission 4 adaptive optic system for the 1.8 meter telescope and Paranal, so that will increase our sensitivity and our accuracy also. But you see already the gain in accuracy procured by gravity. And this is not a miracle on the paper, it's just a matter of the dimension of the sky, of the scale of the instrument. That's the gain between an 8 meter to a 1.40 meter telescope. So on these points we have an accuracy of a few tenths of micro-arc seconds. And you have the fit here made with the gravity points and all the past points obtained with non-adaptive optics and with adaptive optics instruments. So we start to see the curvature just with the gravity points. After a few years of observing, you see that the period of this binary is a bit less than 30 years. So two years of observation is quite tiny at this scale. And we start to see something. And here you have the fit residuals. So the individual points have error bars measured by gravity of a few tenths of micro-arc seconds. But as you see, the residuals are much larger. Hence the chi-squared here, which is on the order of 30. So we don't know yet whether it is because the object is not as simple as a binary, or whether we still have some systematics here which are not well understood with the adaptive optic systems on the 1.8 meter telescope that will help us significantly. But still, despite of that, we already have typical error bars or typical accuracies on the order of 100 or a few hundred micro-arc seconds with the ATs. Well, we don't have the same with the UTs because we don't spend time with the UTs on bright objects like binaries. Otherwise, it would have shown you what we get on the UTs. But that's to show you the improvement compared to past techniques. Okay, so now I switch back to the Galactic Center. And what I'm showing you here are images made of Sgr and S2 during the past 2 years. These are interferometric images with 4 telescopes. So maybe in the room people are used to doing interferometry with radio telescopes or with ALMA, where you have tens and tens of telescopes, of antennas. And so the image quality is very nice. With a 4 telescope interferometer, it's not as nice. As you see, S2 and Sgr look elongated. That's the PSF. The PSF with the 4 telescope interferometer. And what you don't see here, or hardly see, is the level of ripples here due to the PSF also. But still, we can clearly see Sgr and S2, and you have 2 different epochs here, separated by a bit less than a year on S2 and Sgr. So we see clearly the motion, of course, of S2. And we see S2, which is much more important, at distances very close to Sgr. And this is the acquisition, one of the 4 acquisition cameras of gravity. So this is where we see the performance of our adaptive optic system. And this is also very useful for us to see how we place the fibers, the single mode fibers, in which we inject the light to feed the interferometer. And so that gives you an idea of how difficult it is to observe the Galactic Center with an 8 meter telescope. So S2 is here, clearly visible. You have other S stars here, maybe a black hole somewhere, but we don't know. And you have Sgr actually located on the star here, you see? And because of the confusion, it's hard to separate Sgr and S2 and make an accurate measurement of the separation between the two. Which, of course, is not the case at all with the interferometer because of the larger angular resolution. Okay, so we did that. One of the things we did first was to check whether we were able to do some good calibrations of the interferometric data. What you have here is data collected on one of these reference sources, RS16C. And you have the visibility here. You have one important number here is 1. And you have the closure phase, so a quantity related to the phase 0. here. The important thing is that if the source at this angular resolution is non-resolved, is a point-like object, then you should get 1 for the visibility and 0 for the closure phase, which is the case. So that's a check that the instrument is working fine and that the source is not a binary, for example, or a larger object, which would have been a bad source to make a good reference source. And the plot here, so this was our first paper with gravity, by the way. The first slide paper is a search for fainter sources around the galactic center, fainter than S2. And our first conclusion was that there's no star brighter than k equals 17 next to Sgr star and in the region between S2 and Sgr star. And I will come back to that later because we would like to find other stars closest to the black hole, because this is where, of course, you get the largest relativistic effects. So as far as we know now, none of these sources exist. And so we have to rely on S2 for and on flares at the galactic center for test of general relativity. And so this is where came our first result. So one of the big motivations to be on the sky in 2015 with gravity was because we knew that S2 would go to Perrin Center by 2018, in May 2018. Now we know it's May 19th of 2018. And so we knew that we needed some points before Perrin Center, points at Perrin Center, and points after Perrin Center. But the most important point, of course, were before Perrin Center, because they were the most stringent on the consortium. And so this is why we were fortunate to be on time at the telescope and to be able to observe since 2016. The data were not so good at the beginning because we had many things to understand at the telescope, in particular the metrology and the optimization of the fringe tracking system. And so we were able to publish results, first results, based on the data collected in 2017 and in 2018. The other project with astronomy, of course, from the ground, is that the sources are not available all the time, unfortunately. And so the Galactic Center can only be observed from the end of March until the beginning of, or until September. So you have a window of 6 months during which you need to be in Paranal and observe the Galactic Center every 15th day or every month. So the first thing we wanted to do was to detect gravitational redshift with S2. And for that, you need to combine two techniques. You need to combine imaging, so that's what we did with gravity. These images that you already showed, that you already saw. Well, there's one more here. And by the way, this is the very dirty PSF with the 4-telescope interferometer. And you need to combine that with spectroscopy. So we use the Symphony instrument to measure these bracket gamma and helium lines to measure the redshift. This sequence here shows you the positions we measured for in a nice way with gravity during the 2017 and the 2018 campaigns. So this was Perrin Center here. At Perrin Center, the source is 13 milliarc seconds away from the Galactic Center. So it's very nearby. And we've been extremely lucky also because we had not anticipated that initially when we built gravity. But actually, at this time of the orbit of S2, S2 and Sgr star are in the same field of the interferometer, which means that we can directly connect S2 and Sgr star, minimizing systematics on astrometry. This we hadn't thought initially, but it turned out that the telescope to be extremely important and a huge advantage for us. Because otherwise, you need to connect Sgr stars to other sources in the field, and then you accumulate systematics. So this is the orbit which is now known for S2 around the Galactic Center. You have a mix here of gravity points, here, this part here, and other points collected in the spectral interferometry era with SHARP and with NACO here, so adaptive optics. And here you have the spectroscopic measurement of S2 measured in radial, translated into radial velocity, and you see that the star reaches very high speeds, velocities next to the black hole, typically 2.5% of the speed of light. Here you have a close-up of the data collected by gravity with a very nice accuracy. Okay, so the resolution doesn't look very nice on the screen, no? Let me try to improve that. Sorry? Oh, yeah. I thought it would be straightforward. Okay. Well, normally angular resolution is my best, but okay. So what you see here are the fits of the data, spectroscopic data and astrometric data with models. The line here, so the gray line here is the non-relativistic orbit, and the red and black lines here are the relativistic orbits. The black line is taking into account the Schwarzschild precession or the precession, which, as you see, will only be detectable after this paper has been published. So we have no information at that time on the precession of the orbit that we expect. We expect a precession of 12 minutes for the orbit of S2. But it was clear that we could measure the gravitational redshift at a level of 200 kilometers per second, as you see here. So the detection was clear, and well, you could tell me, but what is the need to have the gravity data point here? Well, the need for the gravity data point is that if you don't have these gravity data points, then you have data points with a poor accuracy, and then you can adjust your classical orbit such that you can mimic actually this peak here. So that without the gravity data point, you cannot be sure that the only solution possible to fit both the astrometry and the spectroscopy here, the radial velocities, is a relativistic model. And so we parameterize the model with a single parameter, f. F equals 0 is the Newtonian model, and f equals 1 is Einstein. And what we did that with post-Newtonian expansion. And at that time, we found 0.94 for f plus or minus 0.09, which was clearly excluding the Newtonian hypothesis and favoring the Einstein hypothesis. So at this stage, the measurements are compatible with general relativity as stated by Einstein. So we were very happy because it was the first important result for us. The reddening had not been tested in this regime yet. So what I'm showing now, because this was based on results obtained until June 2018, then we were continuing observing the Galactic Center and S2 in the course of the summer, so up to August, and we were observing also with Symphony. So you have some new points here obtained with Symphony, which fortunately lie on this very nice red curve. So we were very much relieved, and we could extend also. Maybe it's on another slide. Yes. We could extend also the astrometric measurements, And what you see here, this red line, is taking into account the Schwarzschild precession. So we start to see the Schwarzschild precession. And of course, we cross fingers that in a few months from now, the new points we'll make with the gravity on S2 will lie on this red curve. There's still some suspense, we don't know yet. We'll see in March, April. Okay, so if you combine all these points, then you can refine this parameter f. So f equal 1 for Einstein and 0 for Newton, and you see that now this is getting even closer to 1, well, 1.04 plus or minus 0.06. And of course, some of the parameters in the fit are the Sgr mass, so it's 4.1 million solar masses, and the distance to the galactic center, so 8 kiloparsecs. And for the Schwarzschild precession, that's the same. We use this another parameter f, and we find, based on this data, 1.3.0.8, plus or minus 0.8. And we hope, of course, that the error bar here, the accuracy, will increase in 2019 after 6 months of observation. It can only increase because, of course, the Schwarzschild precession is like a kick given to the elliptical orbit. And so the larger the amount of time, the larger the difference between the two orbits. So that at some point it will be very easy to measure the Schwarzschild precession. There is another part of the precession here, which is due to the lens steering effect, which we plan to measure also. The lens steering effect is a frame dragging effect due to the spin of the black hole, and so that's a way to measure the spin of the black hole. From our simulations, it will take a few years before we can put a constraint on this number. This is why also we're looking for stars closer to the black hole in order to be more sensitive to the spin of the black hole. Okay, so that's the first part of the result we got on the Galactic Center. I don't know what time it is. A bit late? Okay. The second result, which is very recent because the paper was just accepted a couple of weeks ago, was first measurements of flares on the near the black hole. The flares are, let's say, stochastic events in the sense that you don't know when they will happen, you don't know if they will happen, and you don't know what will be the magnitude of the flare. And we were expecting bright flares since 2016, May 2016. So we saw a lot of activity of the black hole. The black hole never has the same brightness. It has a strong variability, but we were expecting a very strong variability. And this only occurred this year in May and then July, at last. Exactly at the time when we were publishing the result on S2. That's life, but it was a good surprise. So the flares, the infrared flares on the Galactic Center are very well known also since 2003 in this first paper by Genzel and colleagues. The flares occur on average once a day, so every 2 nights. And some of them can be very bright. This one was extremely bright and pretty much favored the hypothesis of the hotspot orbiting the black hole near the last innermost stable orbit, circular orbit, or on this innermost stable circular orbit. So these are the main hypotheses to explain the flares. Either some stochastic events in the accretion disk around the black hole, or magnetic reconnection in the jet, or the one which is for us the most favorable hypothesis, a hotspot orbiting the black hole very near the black hole. Why do we prefer this one? Because this one we could use as a test mass near the black hole orbit, and it is also very nice to trace the event horizon and have an idea of the scale of the event horizon. These ones would be interesting, but unfortunately the hotspot would move away from the black hole, So we would not learn much about the black hole and about the metric of the black hole. So what happens in practice? There is shearing in the disk here, and the shearing may induce some some crossing of the magnetic field lines, and you have a reconnection event, and this reconnection event releases a lot of energy that creates the hotspot. And then the shearing continues and shears the hotspot, and at some point you don't see the hotspot anymore. And this is interesting because this can occur at scales very close, at a distance very close to the black hole. So we have been lucky to measure 3 of them this summer and this spring, one of which was very bright and allowed us to measure a trajectory. So what you see here on this graph is the flux we collected from Sgr A during this flare event, compared here to the brightness of the star S2. So you see, at maximum, it was on the order of half of the star S2 flux, which is nice. But the brightest flares can be brighter by 1 magnitude than S2. So maybe there's hope for a still brighter flare, which would allow us to increase our accuracy. And what you see here are the astrometric measurements. This point here is the central point of the model, that is to say where we put Sgr A. And here, that's where we find Sgr A based on the measurements we made with S2. So it's not exactly that, but it's compatible within the error bars that you see here. So we have good reasons to think that we see a trajectory around the black hole on a size which is actually comparable to the size of the horizon. The size of the horizon is traced here by the secondary images of the flare. And this is a comparison between, on this slide here, a comparison between the data points that we have measured. These points are the same as these ones, with an orbit here in the case here of a Schwarzschild black hole. So an orbit whose radius would be 7 gravitational radii, or 3.5 Schwarzschild radii. In the case of the Schwarzschild black hole, the innermost stable circular orbit is at 3 Schwarzschild radii. So we are very close to the innermost stable circular orbit. And you see the period here. The period is on the order of 40 minutes, with an orbital velocity for the hotspot here on the order of 1/3 of the speed of light. So we have 2 others. This is the 22nd of July flare. We have 2 others, but the conditions were not as good, and the flux collected on the hotspot was smaller, so the hotspot was fainter, and so the data are not as good as this one. They are in the paper. We shot them, but you don't clearly see an orbit as we see on this one. So we do this comparison, I'm just citing my colleagues here, with a code developed by Frédéric Vincent and colleagues, which is called JOTO. So this is how we compare the measurements on gravity with let's say, with the theory. These are 2 examples here of flaring events. The stochastic one, the red noise here, hypothesis, or Rossby wave, Rossby instabilities in the accretion flow around the black hole. Well, we can do funny things too with that software. We can also pretend that we're observing a black hole which would be located between the observer and the Eiffel Tower. This is for a 1 Earth mass black hole, but at least it shows the magnitude of the effects that are not necessarily easily understandable in these images. This was made by my colleague Thibaut Pomard for outreach purpose. Okay, the other thing we measured, thanks to gravity, is the polarization of these flares. With gravity, we are able to split polarization and to rotate the polarization to measure the Stokes parameters. So we are able to measure the polarizations with our fringes also. And so something we found that was extremely interesting is that the linear polarization we measure is actually also rotating with time on a period which is comparable to the period of the astrometry. And this is also extremely important to set constraints on the phenomenon that we see. So that's the same. We don't have the same level of quality of data for the three measurements we made. Some of them we had the Q parameters, some of them we didn't have, and some others we had Q and U parameters. But on the clean measurement we have, we clearly see this loop here made by the polarization in this U and Q plane, with a period also on the order of 40 minutes. And well, this event also is also important because to measure a loop like that, you actually constrain the type of magnetic field you get. It's a poloidal magnetic field. And you also constrain the orientation, actually, of the orbit. And this one points towards a very low orientation of the orbital plane on the sky. So we see the system almost face on, which is not very good to test general relativity because the beaming effect or the lensing effect are smaller with this orientation. Okay, you cannot be systematically a winner. Okay, so combining the different measurements we've made, so the polarimetry here, so the fact that we measure a loop gives a constraint in this plane here with the inclination and the radius, that's this dark patch here. Another constraint, of course, is the astrometry, and the astrometry also is compatible with a low inclination of the system. And the polarization period also is a constraint on the radius of the event. So you see that they are quite all on par. And you have another constraint, which is the contrast of the flaring event. So I show it to you again. So that's the flux of the flare as a function of time, and you see the contrast is not very high. It's actually on the order of 20, 25%, 30%. And so it means there's a little beaming, little light bending, and this also favors a low inclination. If you had strong inclination, you would have very large contrast in the flaring event. So our conclusion is that whatever the model we use, a Schwarzschild black hole or a Kerr black hole with the maximum speed, or a Kerr black hole with the maximum but retrograde spin or -1 spin, we find that typically the radius of the event is on the order of 7 to 8 gravitational radii. With an inclination probably less than 30 degrees on the sky. That's the first conclusion we can derive from these measurements. And if you put that into a plot where you have the radius of the orbit here and the period here in minutes, so we measure 3 events, we get 3 points, and they nicely align on what you expect for various black holes with either no rotation, that's the red curve, or maximum prograde rotation here of a Kerr black hole, or maximum retrograde rotation here for also a Kerr black hole. So as far as we can say, this is fully compatible with what you would expect for a hotspot orbiting a black hole. But we are not at the stage where we can measure the spin or constrain the spin, essentially because we don't have enough accuracy yet on these data points. or also because we didn't measure a short enough period, for example, which could have allowed us to discard the Schwarzschild black hole hypothesis. So that's for the next flares that we are expecting. So far, this is a diagram here where you have the potential as a function of the log of the mass of the object you're using to test the GR. The S2 reddening has allowed us to explore a new regime here in this area, and the measurement of the flares here allows us to start to explore this region where there were also constraints provided by the K alpha line measured in disk around the supermassive black holes. The difference here with the gravity data here is that this is a direct measurement. Okay, so what's next? And that will be my conclusions. We're still looking for faint stars. And the idea is very simple. Take images and try to be as sensitive as possible. So we are still improving the instrument and the technique to reconstruct images in order to detect these stars, if they exist. If there's no star, there's nothing to detect, but we don't know yet. We still hope. This was a simulation done with Thibaut Pomard 13 years ago when we were thinking of gravity. And at that time we were thinking, okay, we will find some stars closer to the black hole, and we'll be able to measure strong effects, strong relativistic effect. Here that's a simulation in the Schwarzschild case, where you clearly see the precession, and of course on a time scale which is much shorter than the time scale of the orbit of S2, which is 16 years. Here you would get the measurement in less than a year, in a few months, and with stronger effects. So that's the hope we're still pursuing. And if we do that, I see Clifford Will in the room here, so this sounds familiar to you, so this is your graph. If you do that, and if you find stars on orbits of typically a few months and with the strongest eccentricity, that's the eccentricity of S2, then you would be able to test the Noether theorem, which gives you a relationships between the quadrupolar moment, the mass, and the mass of the black holes. So if we find these stars, then we will be able to test this theorem, and this is why we are extremely motivated to go down this line and try to find these objects. There's very little hope that we might succeed doing that with S2. We need to wait for a very long time, and possibly it will not be enough. Well, the simulations we've made show that it may not be possible to do this test. To measure the spin, yes, in 8 years from now, if we don't find anything else, we will have the answer. An alternative is to do that with the flares, but the flares are possibly astrophysical objects which are more complex to interpret than stars. So stars would be ideal object to make this test. I will pass on this. And something we are also expecting is the result of the Event Horizon Telescope. Well, we have a competitor, not in the infrared, but in the millimeter, and it's very nice to have competitors, especially when the competitors are completely complementary to what you're doing. They observe black holes, Sagittarius star and M87 in the millimeter regime in a much larger interferometer than what we can do at the LTI. Since they're combining telescope in Hawaii at the South Pole, in ALMA and NOEMA here in Europe. And they will be able to make images at the scale of the Event Horizon, hence the name Event Horizon Telescope. It will be wonderful to compare the results that we will get with gravity on the black hole and with the Event Horizon Telescope, hoping, of course, that they will be consistent. And apparently, a paper is floating in the air and should be out at the end of the year or beginning of next year. So we need to be a little patient. Okay, thank you very much. And I want to thank my colleagues.
Peut-être nous avons le temps pour quelques questions.
About the search for fainter stars close to S2 or closer, in view of the mass segregation problem, do you expect really easily to find fainter stars?
Not
or
at all.
More white dwarfs?
Well, I doubt that white dwarf we will see them. And fainter stars, well, the S stars are OB stars. So fainter means probably smaller mass stars. So A, maybe, stars. A stars, F stars. And they should be at magnitudes around 20. So we need to increase our sensitivity and our ability to combine interferometric data in order to build up a signal-to-noise ratio to reach these magnitudes. So in the first flight paper, we published that we could not see anything down to 17 in K. Today it's 18, and so far we have not seen anything. So many times we thought that we were seeing something moving, comparing bad images with other bad images, but nothing sure, and honestly there's nothing as of today. So we are patiently collecting data, we are patiently saving images on disks, well, data on disks, with the hope also that we will improve the image reconstruction algorithms in order to improve the image quality and succeed to see these stars, if they exist.
On the polarization, what is the model of the polarized emission?
So it's a synchrotron emission, yes. And we tested two types of fields, so a poloidal field and a toroidal field. And the discrepancy is very easy between the two fields because in one case, the period corresponds to the period of the flare, so 40 minutes in our case here. In the toroidal case, the period is half of that, so it's about 20 minutes. So the fact that we see the same period points in the direction where we see a poloidal field.
And does that also, the brightness of the flare and the polarization degree, does that give you magnetic field strength?
That's a very good question. I'm not sure we have that.
Very impressive.
We know that the field has to be strong in order to be able to survive on this time scale. Yes, but I'm not sure we are in a position to give the magnitude of the field.
Might be coming.
Yeah.
Yes, sorry to go a bit further out than our own galaxy. What are the prospects of measuring the structure of active galactic nuclei like NGC 1068 or something like that?
Okay, so we have a result. I cannot communicate on that, but we have a very good result. I cannot show it. We have a paper accepted in Nature, and that's what we were dreaming of since when I was doing experiment in Hawaii. I was dreaming of characterizing the broadline regions of AGNs. So we have one. First one.
So do you have an idea of the mass of stars that orbiting around the supermassive black hole in Sagittarius stars?
So, well, the S stars are OB stars. So if you
yes, but the mass of stars.
You mean the total mass?
No, the mass of every stars.
Yes, it's 8 to a few tenths of solar masses.
So it's stars. It's a massive stars.
Massive stars. Absolutely.
All the stars around the black
all
hole
stars
are
massive stars.
Okay.
That's one of the elements of this paradox. They are all young stars and all massive.
Hello. So I was wondering, when you say that you can constrain the spin of the black hole, can you just constrain the amplitude or the orientation as well?
Sorry?
For the spin of the black hole, when you will constrain the spin in a few years, will you just constrain the amplitude or the direction as well?
No, we'll constrain the direction also. Because we will be For example, if we are, well, we already have a constraint, by the way. If it's a spinning black hole, we see a system from the pole or close to the pole. And if we manage to measure more accurately some orbiting spots, as you see, for example, in this image of the Event Horizon Telescope, in this little movie here, they are tilting the tilt, and you see that the lensing effect and the beaming effect depends on the orientation of the black hole. So that's also what we will see and what we start to see with the gravity data. But to do that, we need to improve our error bars to be able to be really sensitive with respect to the models. So far, we've compared models with various spins, and they are compatible with the data we measure. So we're not stringent enough. And the reason why we're not stringent enough is both the geometry, which is not favorable, but also the accuracy of our astrometric measurements. So the plan is to work on that. I have a video conference this afternoon to devise a way to improve our error bars. We are a factor of 2 or 3 with respect to what we were contemplating initially, which is already very good. But now we see with this first result that we are still on the verge. We're not yet on the other side to be able to bring a full constraint.
So thank you very much, and I think we can congratulate again the speaker for this very nice result.
Thank you for coming, and thank you for staying.